Okay, so we left off last class talking about a specific discrete random variable, which was the binomial. So we worked through a bunch of different examples. I showed you how you can do it in Excel. So a couple things I'll talk about before we get into the next example is I think we should finish the Poisson today, and then I'll start kind of talking about the uniform and finish the uniform distribution on Friday. I'll also try to get up, be recording a couple short videos that go over like in segments like 4 or 5 of the practice exam questions. We'll go over those Monday as well. So the way that the exam's going to work is I'm going to open it up really early Monday morning, probably like 7 or something. I don't expect many of you want to take it prior to that. So if you want to take it without watching that additional kind of review on Monday, you can. It'll be open the whole day Monday, and then it'll be open the whole day Tuesday. Right? So I'm still kind of in the process of getting the final details on it. You'll have somewhere between an hour to an hour and a half to take it. It'll be mostly multiple choice. And then the last question will be maybe a short answer with a couple different components. So what I want you to do there is, however you do the work, you do that by hand. You can just take a photo and upload the photo. If you want to scan your work and upload it, that's fine as well. I don't know how many of you have access to like a scanner while you're taking it, but I think for the most part, usually just, most of you probably have a phone or something you can kind of take a picture and quick upload that. Or you can upload an Excel file where you did your work, or type out kind of what you did in Word. All those are options, and you can upload those for that short answer portion. I don't think we'll be using Respondus for it because I want you to have access to Excel. I want you to have access to that formula sheet. I know there's ways you can kind of click the links in there. I played around with it today, and it's not the version of it. I couldn't get some of the Excel functions to work correctly, so I'm not sure exactly what's going on there. It doesn't allow you to really use Excel. You can observe things in it, but there's something kind of weird going on, so I probably won't be using that. Going by the honor system, I'm just kind of trusting that you're all taking individually. If I start to see things on the short answer portion that look similar, it's going to raise some alarms for me. There's also other things I can do, like maybe you won't all see the exact same question. Questions will be in different order. Might see slightly different kind of answers, and so I'm going to trust you though, kind of academic integrity to take it on your own. Like I said, once you take it, you'll have a certain amount of time to submit it. So because it's due by the end of the day, Tuesday, if let's say I give you an hour, that means don't start it later than, give me 1 second. You won't be able to start it later than 11 and get that full hour, right? Because it'll close you out at midnight. So even though it's open till midnight, start it, or don't, hopefully you aren't starting at 11 o'clock at night anyways, but I've seen crazier things. So hopefully, like I said, a lot of the questions look very similar to those practice exams. Like I said, I'll put out some short videos that go over some of those problems that we won't be able to go through Friday and Monday. Okay. Any questions for me? So where will upload the Excel sheet? Are you referring to the short answer question? There'll be kind of I don't know if you've ever seen it in other classes if you haven't used it, but I can insert an option where it allows you to upload a file. So it would be just like you were, you'll have an upload option just like you would upload it for an assignment. Yeah. It's pretty obvious that it's there when I add it in. I'm assuming that was the question about the exam. I'll upload the Excel sheet. If it wasn't, type in the chat and I can answer if you're talking about something else. Any other questions for me before we kind of jump into things here today? Okay. Oh, okay, I got it. Good. All right. So the next type of discrete random variable that we'll talk about is the Poisson. So when we're dealing with a binomial, it was always how many successes out of a certain number. So, right, the probability that we see 5 successes out of 50, or the probability that we see 10 successes out of 100. So we were always capped at the total number of successes we could see, right? I'm looking out of 100, the most successes I can see is 100, right? The Poisson is going to have an open-ended kind of, you could see theoretically an infinite number of successes, or another better way to think about it is a very, very large number of successes, right? and you're not looking at kind of this capped amount, you're looking over an interval, right? Over a space. Usually this is time. The examples that I would use on the exam will all be time examples. We'll go through one in class today that's a physical space, so it doesn't just have to be a time interval. It could be over a mile, over a vat of 100 liters. It could be some type of physical space as well, but more often than not, the examples I'm going to give you, and the only examples I'll give you on the exam will be with time. Okay? So what has to be true, and I'm not going to spend too much time on these because every example I'll give you will fit this, is that if we look at over any equally sized interval, so let's say I'm looking at an hours, right? In any given hour that I choose, it has to be that the probability of seeing a certain number of successes over that hour is the same for every hour in the day. So a Poisson distribution would be a terrible approach to looking at alcohol sales at Brothers, right? Because the alcohol sales from 2 to 3 p.m. are going to be very different than 2 to 3 a.m., right? So, or actually, I don't know how late the bars are over here, but you get the idea there, right? So if they don't overlap, it has to be that they're also independent. So it doesn't matter what the sales were in the first hour. It doesn't impact the probability of seeing different number of sales in that second hour. Right? And then the question that we might want to ask is, well, I typically see, I don't know, 100 drinks sold over this 1 hour time span, right? What's the probability in the next hour I see only 50, right? And so we're still going to be interested in the probability of seeing a certain number of successes. It's just now it's not out of a certain number, it's over a given interval, okay? So it's the same kind of, we're still looking for probabilities, so we're going to need some probability mass function. It's not going to be that binomial equation that we're using. Instead, it's going to look something like this, right? Now, this is actually really a lot easier, and some of this stuff might look goofy, but this is way easier than the binomial, right? Because lambda is just going to be something that you're given, right? So lambda here is from some historical data or something you're told. You typically see lambda number of occurrences over that interval. So this would be, I'll use another example. Let's say we're thinking about car accidents out on McGalliard. Maybe every week there's 10, right? On average, there's 10. That would be your lambda. Based off of history, we know on average over a given week on McGalliard, there's 10 accidents. Right? X would then be, okay, I'm interested in what's the probability this next week, right? Because we're still dealing with a random variable, something that hasn't happened yet. What's the probability that over this next week I see 12 accidents instead of 10, right? So X is going to be what you want to find the probability of, the number of occurrences. Lambda is going to be some average or mean you typically see over that interval, so that has to be given to you. So really, I mean, you've got two things going on here, and then this E is just some natural number. It's kind of like pi, right? It's 2.718281828. There's a bunch of different ways you can kind of memorize it. I think there's some way you can do it with like Abraham Lincoln's like facts and memorize it out to like 20 spots or something. But it should be on your calculator, right? In fact, in Excel, you think you use EXP or something like that. We'll check it out here because I'll go to Excel in a second, all right, when we get done with this discussion. But it's also, if you're not real comfortable with it, you could take it out to that 5th decimal and just use this number. But it has it stored in your calculator already. If you can't, once again, it's kind of similar to the factorial. If you can't find that on your calculator, let me know. I think it's 83, 84. You might have to hit second, and then it's kind of it's above one of the other buttons. But it should be somewhere on there. So, like it should be like written on there for you. So it's not like we had to find the factorial. It's actually written on the calculator. The only other thing we have then is this factorial, which we've already talked about. And it acts the exact same way. If I put 5 in as x, 5 factorial, 5 times 4 times 3 times 2 times 1. So really, this is a pretty easy equation once you get all the numbers plugged in, and that you don't forget there's a negative sign here. Right? So there's an e to the negative whatever lambda is. So we'll work through a couple examples here. So this first one, this guy wrote the law of small numbers. He's a brilliant guy, whatever. So he had this example where, on average, in the Prussian army, 0.61 soldiers were killed every year by horses, right, in some accident. Okay? So 0.61 is kind of the typical number of people we saw get killed by horses every year. So our time interval is a year. Our lambda, the average number we usually see, is 0.61. And then we might be interested in something like, well, what's the probability I see exactly 3 people killed this year? Well, it's definitely higher than the average, right? So I know that the probability isn't going to be as likely as, say, 0 or 1. So this works very similar to the binomial in that whatever the mean or the expected rate is, which here it's easy to find the mean because it's just given to you, right? This is the average or the mean you typically see over that interval. So if the mean is 0.61, we know that the most likely outcomes would be 0 and 1, because it's still discrete. We can't see 0.61 people die. We either see 0 or 1 in this next year. And then as we move away from that expected value, 3 is kind of moving away, that probability will start to decline. So we want the probability, so what are lambda and x? I kind of already mentioned this. Lambda is just that rate you're given, the average you have seen in the past over that 1-year time interval. So that was our 0.61. We're interested now in finding the probability that exactly 3 people are killed. It's just a matter of plugging those 2 numbers in. Right? I mean, it's the same as the binomial. Once you have what you're looking for, it's just a matter of plugging those in and getting comfortable using your calculator to find this. I think this is a lot easier than the binomial personally. Once we start working on it, we'll see that actually, I think it is. But it's as simple as that. And there shouldn't be 2 f of x's here. I probably hit Control V twice in accident. Okay, any questions on that? We'll work through a couple other things I think are more complicated with a Poisson, but I think this part of it's pretty easy. Right? It kind of follows what we were doing last class, but just a slightly different formula. So kind of notice here we get a pretty low probability. What would happen if I wanted to find the probability that 4 soldiers are killed? I know that would be smaller, less than 0.02, because I'm moving further away from that expected value or that mean of 0.61. I mean, if you're telling me on average, not even 1 soldier is killed every year, right? 0.61. Well, what's the probability that like 10 die next year? Well, really, really, really small, right? I mean, if I usually don't even see even 1 on average, probably seeing 10 is going to be very low. So, all right. So let's say we had a different example, and I've got births at a hospital. So maybe I'm worried about staffing, right? And I know that on average, my hospital experiences 1.25 births every hour, right? Well, I want to make sure that I have enough people on staff if I see more than the average, right? Especially if seeing more than the average is somewhat likely. So if I have this average rate over the time interval of an hour of 1.25, what's the probability I see exactly 3 births in this next hour? Well, my lambda here would be this average rate I'm given, 1.25. The number of occurrences I'm interested in finding the probability of is exactly 3, so my x is 3. And now it's just a matter of plugging those values in, right? I go back to this equation. Excuse me, my lambda is 1.25. My x was 3, did I say that? Yeah, 3. And then I have that natural number e that's always the same number. Kind of just like pi is always the same number. Now, I probably can't rule any of these out, just looking at these. If I saw something like, here's kind of a tough one. Is there any value you could probably bound this probability at? Like, it probably has to be less than a certain value. Well, if I think about the mean as 1.25, what would be the most likely outcomes for me to see? 1 and 2, right? So those are the most likely outcomes for me to see, but I could have also seen 0, 3, 4, 5, 6, 7, 8. Even if these, 1 and 2 had a likelihood of occurring of something like 0.25 each or about that, I'm probably thinking the probability of seeing 3 then, I'm only left with 0.5 left, right? Because the sum of the probabilities of every outcome have to add up to 1. So I'm thinking it's probably less than 0.5. All these are, of course, but if I saw something here like 0.7, it should kind of be alarmed, right? In fact, if it was 0.7, it doesn't make any sense, because if it was 0.7, there's no way that 1 and 2 could be more likely, right? Because I've only got 0.3 left to play with. So when we're thinking about values that are further from the mean, if I'm seeing something here that's like over 0.5, I should be a little bit alarmed about that as a possible answer. Especially if I come up with an answer, I probably made a mistake in my calculator. But really, it's just a matter of plugging those values in. Once we do that, we get that 0.09. So what would that have been? I think out to the second decimal, 0.093. Okay. So if the probability that x is equal to 3 was 0.09, what do I know is true about the probability that x is equal to 2? has to be greater because I'm moving closer now to that expected value or that mean. Right? So this is just kind of repeating some of the same stuff, but just to kind of solidify these ideas. Right? All right, so this is where we start to get a little bit more tricky with it. What's the probability that I see 2 or more births in an hour? Okay, so I get the same kind of typical rate of 1.25. Now I want the probability I see 2 or more. Well, if I write this down, stop this here. I think about what I'm looking for. I said I wanted the probability that I see 2 or more births. So this is the probability that x is greater than or equal to 2. All right? What are all the, it's just like the binomial. I either see exactly 2 births, exactly 3, exactly 4, so they're each have their own probability, and they're each mutually exclusive. I can't see exactly 2 or exactly 3. I can only see one of those. So what outcomes fit this criteria? I could see 2 births, or I could see 3 births, or I could see 4, 5, 6, but where do I stop? I guess like the population of the county, or, right? Like I don't know, right? It's over a given time interval. So if I'm looking for this probably being greater than, I can't do, I mean, there's no way I can do this. So what's one way, but I can solve this, just not in the way I described. So what could I do here? Similar to the binomial that we talked about. If this is A, what else could I do? Yeah.
You find the Poisson of 1 and then subtract the answer from 1.
Close. You're thinking about this right. What else did you forget? 0. You can't forget about 0, right? So we want to think about this is the probability of an event is 1 minus its complement, but the complement is being less than 2. What are all the outcomes that fit this criteria? Well, if it's less than 2, it could be 0 or 1. So we would then have probability x is equal to 0, probability x is equal to 1. Right? So we have to use that Poisson equation twice, but at least we don't have to do it like an infinite number of times, or whatever to the population. So with the Poisson, it's a very similar principle as the binomial. It just becomes a lot more apparent that if we're looking for the probability of being greater than a certain value, we're definitely going to have to use this complement rule, right? Any questions on any of this? Also, for those of you in class, if you're looking at this is backwards. So I would always suggest, I see someone looking at, look here instead, right? It'll be a lot easier, okay? No questions on that? All right, yeah, it's really the same, similar principles as what we did last class, just a different formula to find those probabilities. So here I can rewrite the probability of A as 1 minus its complement. What fits this criteria? That was just 0 and 1. So I plug in once, x is equal to 0, find that. Plug in x is equal to 1, find that probability, add them up, and then subtract them from 1. Okay? Now, kind of one thing to remember is to point out again, what should 0 factorial be here? 1, anything to the 0 power, 1. So this actually, I don't really need to enter these in if I don't want to. It should just be e to the negative 1.25. Okay? So you can kind of simplify some of the things there. Also, what's 1 factorial? 1. So I don't really have to enter that in my calculator and possibly make a mistake. So if we do that, we get about 0.355. Okay? Any other questions on this one? Now, one thing I should have maybe been thinking about is, this probability of x being greater than or equal to 2, if we had an expected value, of 1.25, I said the most likely outcomes would be 1 and 2, but since we're closer to 1, the most likely outcome is 1, right? And so we're going to be missing that pretty likely outcome of 1 from our probability. So to get something as high as 0.8 probably seems like that's a little bit too high because we're missing the most common outcome of 1. And really 0 isn't very far from 1.25, so we're missing a pretty common outcome in 0 as well, right? In fact, if we wanted to map this out, we would see that zero is not a whole lot less likely than seeing 2, right? You think about it, right? We're only 0.75 away from 2, and we're 1.25 away from 0. So those are fairly likely outcomes. And 0 and 1 are not included in this. So to see something as high as 0.8 doesn't make a lot of sense for us here. But other than that, probably couldn't rule anything out here. C is very unlikely because 2 is a pretty common outcome, and you're taking not just the probability of 2, but everything above 2. So to see something as low as 0.03, like I said, theoretically, maybe we shouldn't cross it out, but it seems like a pretty unlikely answer. If I was just trying to guess without using the formula, I'm thinking B or D are probably my best guesses here. And I talk through these things just because, like, when you're sitting down to take the exam, thinking about these things ahead of time before you enter all your numbers into your formula can help you, prevent you from making some easy mistakes. Because I'm sure some of these up here, for instance, 0.86, it's probably like if I move the equality on the 2 or something like that. So it can kind of help you from making mistakes like that. Any questions on this before we move forward here? You good with that? Okay. So we can think about what different Poisson distributions look like. As we have lower lambdas, right? Lambda of 0.1, 0 and 1 would be kind of the most likely outcomes, but 0.1 is very close to 0, so 0 would be a very, very likely outcome, right? And then seeing any number of occurrences higher than 0, would the probability to decline pretty quick, right? Because if on average I only see 0.1 of something every year, the likelihood I see 3 next year is very low. I usually only see 0.1. How am I going to see 3? And then as that lambda grows, you can kind of notice this starts to look more, it's always right skewed, but as lambda gets higher and higher, we start to get something that's starting to approach more of a normal distribution, right? So if I had a higher lambda, it's going to kind of move to being less and less right skewed there. Okay? I think that's all I really want to say here, but I've already mentioned this, but the mean for our Poisson, very easy. It's always going to be given to us. It's just lambda, right? That's the mean or the expected value. Okay? The expected number of successes over the time interval is lambda. Our variance, so this is a really weird property of the Poisson. Once again, we could Google the mathematical proof. It doesn't matter what lambda is. We can walk through it and we'll always get that the variance is actually also lambda. That's a really, really weird property of the Poisson, but in like higher mathematics, it also makes it a very useful distribution when you're doing certain things. And then the standard deviation, as always, whoops, just to take the square root, right? So the mean and the variance of the Poisson are the same, so that makes life a little bit easier. Probably don't really do a whole lot with the variance here, and for the sake of what we're doing in this class, but that is a property of it. Okay. All right, so let's go back to this binomial distribution and think about maybe relating these two. So let's say I have this huge mass of what? A radioactive substance. I've got 10,000 atoms, okay? The probability that any one atom will decay in a 1 minute time period is 0.0005. So what's the probability I see 3 atoms decay in this next minute? So this one, we do have a time interval, but notice we also have a cap. Because if it's a success failure, seeing it decay as a success, not decaying as a failure, we know that we have 10,000 atoms, so we do have like a capped amount of atoms we could see decay. And the probability that any one atom decays is 0.0005. So I could set this up as a binomial. My probability of success, 0.0005. N, 10,000, and I want the probability that exactly 3 decay. Okay? Well, if I write this out as a binomial, I mean, I've got 10,000 factorial. Obviously, we've talked about a lot of these things can cancel, right? But assume I had a slightly different example where maybe I'm not interested in finding the probability of 3, but I want to know the probability that 100 decay. Well, then I'm still left with a huge, number up top and a huge, I might not be able to actually do this on a normal calculator. It's going to make my life a headache, right? These factorials are pretty annoying. Now, if we were able to, you probably can't do this on a calculator, but we probably could do this one because we can cancel out enough things, right? Everything past 9,997 would cancel. So if we enter this into our calculator, we will get 0.14, but there's kind of a shortcut that makes it a little easier. So if you're just doing a factorial, it's 60 something, right? But think about an example where I was looking at if 100 decay, I would have, it would actually, I don't know what the limit is on the other side because you have to think about what you're cutting out. To take 10,000 times 9,999 times 9,000 all the way down to 9,000, that for sure is going to be way larger than even 50 factorial, right? Because you're only going 50 down. So I don't know, where the limits are kind of depends on the numbers. And, I didn't want 3 here and instead I wanted 100. I can almost guarantee you your calculator is going to yell at you if you try to do that. Right? So what's a way we could do this instead? If we have a really large number of trials, I kind of talked about like in the Poisson, when we're looking at the birth rate one, I said, well, where do we stop? Well, technically, maybe it would be the population of, female population of the city within a certain age group. So it might be a really, really large number, right? And if my probability of success is really, really low, what actually ends up being true is the number of successes follow a Poisson distribution. So even though it truly is a binomial example, right? We do have a limit. We can actually treat it as a Poisson and we'll get approximately the same answer. I'll give you a visual real quick of why this is true. So here we have a Poisson that has a mean of 0.5, right? So kind of notice what it looks like here. Now this one, it has, we went out to 10. If I go back to last class, there it is. Oh. If I look at a Poisson that has a mean of 5 times 0.1, so 0.5, notice it looks kind of very similar. So we start at like 0.6 and it declines. If I go back down to my Poisson that had the same mean, maybe eventually. Kind of notice it starts out around 0.6 and declines pretty rapidly. So there's a visual, if you actually compute all these numbers, but why, it's a good approximation. It'll get you very, very close. So how do I treat a binomial example like this as a Poisson? All I do is find the mean of this binomial, which is very easy, right? That would be the number of trials times the probability of success. So 10,000 times 0.0005. Once I find that mean, that is now I treat as the mean of my Poisson distribution. So I started out with a binomial. I had, these crazy factorials, really high number of trials, really low probability of success. I'll find the mean of that binomial and treat it like the mean of a Poisson, right? So I'll set lambda equal to that equation we had for the mean of the binomial. Once I do that, I've got lambda is 5. Well, now I've got the probability of seeing exactly 3 atoms decay over the next minute, over a given time interval. And so I can use that lambda of 5. My x will be 3, and those are the only 2 things I need to find the probability using the Poisson equation, right? Lambda was 5. The x I was interested in is 3, finding the probability of x is equal to 3. And I get the exact same answer that I found using the binomial equation. Now, it's going to be off if I go out to like, I don't know, 6th or 7th decimal point, but it's a very, very close approximation, right? Good enough for, my dad always said, good enough for government work, right? So like, we're getting pretty close, okay? And I would not, I'm not going to give you something like that in the exam where you have to convert a binomial to Poisson, but it is an interesting thing. We do want to start to think about distribution approximations because we'll use that in some stuff we do later in the course. That some distributions, if certain criteria is met, they're very close approximations to other distributions. So the binomial, if we have a really high number of trials, really low probability of success, we can kind of approximate that with a Poisson distribution. This is kind of a fun example showing that. So we think about different scenarios where we can use the Poisson, just to give you a few different ideas. Let's say I wanted to find the one that's not correct. The first one, so the probability of a certain number of accidents occur on a highway on an entire day. Kind of already used this as an example, right? If I know the average rate or the average number of accidents that happen, well, that's my lambda. I could then very easily, I'm dealing with a time interval of an entire day, could very easily find the probability of seeing different number of accidents. the probability that a stock return exceeds 10% in a given year. So this one, you might see the time interval initially and think, well, yeah, we can do that. We have a year period, and we know the probability that a stock exceeds 10%. But remember, when we're dealing with this Poisson, even the binomial, we're looking for a certain number of successes. Saying that it exceeds 10%, it's only, we can't see that multiple times, right? The stock is either returning 10 or not. And so this is going to be one in which we can't really use the Poisson here because we're not looking for a certain number of successes. You're looking for is this value over or under, 10%. So that one's going to be the one we can't use it for. We could maybe think of one similar to this where I could use it. Let's say I had a portfolio and I said, how many of the stock, if each stock had the same probability of returning a positive amount, right? I could then say how many of the different stocks in my portfolio return a positive or have a positive return in the next year. And there I'm looking for the number of different stocks, but the way in which we have this one, we couldn't use it, right? The probability that a certain number of calls come into a call center over a given minute. Well, if I had previous data, I know on average how many calls come in. This would be another great example. We could use the Poisson. We got that minute time period. And then insurance companies, what's the probability a certain number of claims come in over a month, a year, however we want to define it. That'd be another great example. So you can kind of see, insurance companies are definitely going to be using this a lot. Call centers, right? You want to make sure you have enough people staffed to take however many calls, especially if, the probability of seeing 50 calls is relatively high. I want to make sure I have enough people to be able to handle those calls. And also if, you're thinking about people being staffed to take care of accidents, whether or not this is police officers, right? You think about the number of crimes coming in a day or something like that. You can find the probabilities of seeing all these different number of crimes and then make your staffing decisions based off of that. So this is a pretty relevant discrete random variable to talk about, right? It has a lot of applications. I have one more example here from this Guinness guy, and then actually, where are we at in time here? All right, I'll go through this one a little quick because I want to walk through some other Poisson stuff before we get out of here. So there's this guy, I forget, I don't know what this letters stand for anymore, but W.S. Cassette. He was hired by Guinness as a brewer, turn of the century, no real formal training in statistics, but in aiding in the brewing process, he discovered that the particles in kind of the beer that they were brewing followed a Poisson distribution, right? So if we look at the particles per milliliter, I think specifically he was looking at the yeast particles per milliliter, he noticed that he sampled them from this huge vat of liquid, right? This huge thing of beer that they're brewing, that it actually followed a Poisson distribution, right? So he was a real brilliant guy, come up with a bunch of discoveries. In fact, we'll talk about one distribution later on that he actually helped discover this family of distributions or come up with the idea. But because he had no formal training, no real education or degree, they didn't name it after him. Like the normal distribution, I don't know if you've ever heard about, is also called the Gaussian. Gauss was a person. Well, here instead of naming it the Cassette distribution, they just called it the student distribution because he had no formal training. So this is the background. I don't know, he probably made a bunch of money. So what he noticed was, if I'm wanting to test this huge vat of liquid that I'm trying to brew, right? Well, the problem is I can't test the entire space. Like let's say I have, I don't know, a couple hundred liters. I can't test each individual milliliter of that huge vat, but I can take out a milliliter at a time, right? So if I take out a milliliter at a time, he noticed that the concentration on average was 10 particles per milliliter, right? So he would sample 1 milliliter at a time, record how many yeast particles were in that milliliter, and he noticed that after doing, I don't know how many times he sampled it, but over a large number of samples, he realized the average was 10, right? But he also noticed when he recorded, sometimes he didn't see 10, right? That was the average. Sometimes he saw 9, sometimes he saw 8. So he recorded all these samples and then essentially built a probability distribution by just like we did. Building a frequency distribution for the number of times he saw 0, the number of times he saw 1 particle, 2, 3, so on. Then turn those frequencies into probabilities by dividing by the total number of observations. And he noticed it's following this Poisson distribution. Oops, sorry. Actually, I went back. There you go. So if we know that it followed a Poisson distribution, and I know that on average over a milliliter, This is kind of a weird one where I'm not looking at time, I'm now looking at a physical space. Over this milliliter of space, on average, I see 10 particles. What's the probability I see exactly 8? Well, my lambda is 10. The x that I'm interested in is 8. And so it's just a matter of plugging those values in, and we get about 0.11. Right? So just plugging in, chugging, because it's a Guinness example. Yeah, anyways. But, if we look at these values, we should automatically think about the average is 10, right? The average is 10 here. So as I move away further from that, the probability falls. And I also know that the 10 would be the most likely outcome. So when I'm looking at these options, C seems way too high, right? If 10 is the most likely outcome, 8 couldn't be as high as 0.3 because that would make it the most likely outcome, right? We would only have about, what, 0.17 probability left to get to 1. So we could rule C out right away. From the other options, just looking at the numbers, and it's hard to kind of envision what this Poisson is doing exactly. I probably couldn't make any better, more educated guesses, but I could rule out C here. Okay? Any questions on that one before we keep moving? Just another example. Good with that? Make sure I see it. Got nothing in the chat. Oh no, I always love this meme. I heard the joke about the Poisson distribution. It's pretty fishy because Poisson is like fish. Is it French? Anyone know French? Yeah. All right, my jokes aren't hitting today. But so I think I've got this like example that maybe we'll run through if we get some time. Or maybe I'll even do it on Friday, kind of to end the class. But I do want to work through something else that we could see with these Poisson examples. And it's a little tricky. Right? So let's say that I tell you on average, the number of people that get like eaten by sharks and killed every year is, I'm going to use some easy numbers, so these probably aren't accurate, but let's say it's 7. Right? So this lambda is for a year. Okay? If I then asked you what's the probability that like 10 people are killed by sharks this year, that should be pretty easy now that we went through these other examples, right? Because my x would be 10, my lambda would be 7. I look at that Poisson distribution equation, I plug in, and I'm good, right? But what if I asked you, what's the probability that, let's say, three people die this month? Right? So if I have the average number of people that die every year, as long as, and I'm assuming that probably not great in my shark example, but I'm assuming that across the months there's no difference trends, right? Or the averages are the same across the months. How could I find this probability? If I know the average over the year, how would I find the average over every month? Yeah, right? I would just divide it by 12, right? I'm just converting my mean or my average to be whatever the new time interval is. And now it's pretty easy because now I've got x is equal to 3. My lambda is 7/12. Kind of a terrible one. I was thinking 7 because I was going to do every week, but then clearly not that many people are killed by sharks. So, but right, here's my new lambda. Here's my x. Now I just plug it into my Poisson and I'm done. Right? So we can do these conversions in terms of time intervals. If we're ever moving to a smaller time interval, right, year to a month, we'll always be dividing by something, right? And that kind of intuitively makes sense, right? If I'm saying on average there's 14 accidents every week, how many on average happen every day? Well, there's 7 days in a week, 14 divided by 7. On average, there's 2 every day, right? So anytime I'm going to a smaller time interval, I take the lambda I'm given and I divide it by whatever that conversion is. And if I asked you a question like this in the exam, which I might, I'm not going to give you anything that you won't know, right? So it's typically I'm going to do something like year to a month, right? Divide by 12. Week to a day, divide by 7. Day to hours, divide by 24. Hopefully it's these times that we all know. And I might even be like, put a note in the question, like, remember, there's this many hours in a day or something. But it'll never be anything like, I won't use any, I'm always gonna be using time intervals. So I'm not gonna be using anything where you're like converting, I don't know, miles to yards or something like that, right? Or you might not remember the exact number off the top of your head, okay? Now, what happens if I want to go instead, let's say the number of people that are killed by lightning every month is 2. How would I find the average number of people that are killed every year by lightning? Also, this looks like lambda. Hold on. 2. How would I kind of do this conversion? If I'm going to a larger time interval, I don't divide by whatever my unit of kind of conversion is. I would then multiply by 12, right? So just 2 times 12. So if I'm going to a larger time interval, right, I multiply by that conversion factor. If I'm going to a smaller time interval, I would divide. But then once I convert it to my new lambda, now it's easy. Right now I've got my lambda, I've got the x in there, it's just plugging into Poisson just like we were doing in the other examples. Okay? Oops, any questions on that before we keep moving? You good with that? All right, let me make sure there's no questions here. Where's the chat? There it is. Okay. And where are we at on time? Oh, perfect. Okay. Let's do this because it's kind of fun. I might get out of class a little bit early. So let's say we're going to be going back a little bit, kind of taking a step away from the binomial and Poisson stuff for now, and going back to talking about some things about like independence. But what's the probability that we have at least 2 people in this class have the same birthday? So I think the numbers I have here aren't going to line up with this class specifically. I'm actually thinking about a class that would have 40 students, right? That's typically what my enrollments are. Okay? So let's say, what's the probability that exactly 2 people in this class have the same birthday if we had to guess what these are between, right? Typically, if I'm like using iClickers and doing some polling, usually people think about this is going to be a relatively low probability, right? Let's say I had 40 people in this classroom. What's the probability 2 of them have the same birthday? Like, there's no way, right? It seems like it'd be a low probability. But as long as we don't have twins, and as long as any day of the year is equally as likely to be born on, we can actually, or we can also think about, you know, how many people do we need to have in a classroom, right? If I had 1,000 people in a class, right, then the probability that someone has the same birthday is going to be higher, right? So how many people would kind of push us past this 0.5 cutoff? That's another question we could think about. So if we think about this as an event X, what we really are saying, what's the probability 2 people have the same birthday? Okay. Excuse me, if I rewrite this, and I say 2 people, at least 2 people. Okay. If I rewrite this as 1 minus the complement of at least 2 people having the same birthday is that nobody has the same birthday. Or another way to say that is everyone has a unique day they were born on in the class. Okay. So I'm going to start going through, and let's say I had like 40 people, and I start just going through each person. And the first person, I say, what's the probability that that first person has a unique birthday? Well, I haven't looked at anybody else yet, so the probability is there's 365 days they could be born on, so 365 out of 365, right? The probability they have a unique birthday, the very first person would be 1. What about the second person? Well, for them to have a unique birthday, it can't be the first person, so there's only 364 days left. So 364 out of 365. And then the third person, 363 out of 365. And then I did this for a smaller class, so 35 people, right? Instead of 40, sorry, I got my numbers mixed up there. So I could go all the way down to that 35th person, find the probability that they have a unique birthday. There would just be 35 days they couldn't have a birthday on. I now have the probability that person 1 has a unique birthday, and person 2 has a unique birthday, and person 3. Well, if I think about this, if everything is independent, right, then to find the probability of the intersection, this and this, I just take, right, the probability of A and B would just be the probability of A times the probability of B. That was one of the kind of byproducts of things being independent. So to find the probability that nobody has the same birthday, X complement, I just multiply all these probabilities by each other, right? So that would give me the probability that person 1 has a unique birthday, and probability that person 2 has a unique birthday, and so on and so forth. All right. So if I do that with a little bit of algebra, we kind of could convert this into another formula with some factorials. I won't go behind all the math that's behind that, but we can. If we look at this, we could rewrite it. Or I could just literally multiply these probabilities by each other. I get about 0.18. But remember, x complement is the probability that every person has a unique birthday. X was the probability that at least 2 people had the same birthday. So we still have to subtract this from 1. So the probability that 2 people have the same birthday in a class of 35 would actually be like 80%. Okay? So it seems like that's crazy high. But if you think about it, if every single day is equally as likely, any given day has a pretty low likelihood of occurring. We get kind of this counterintuitive result, especially with a class that is as high as 35 people. Right? In fact, if we kind of back this out, the number of people we need in order to make it more than like a 50-50 shot is 23. So like if I'm a betting person, if I'm in a room with more than like 23 people, I try to get someone to bet me that nobody has, or I try to get someone to bet me that 2 people have the same birthday, right? Because it's going to be a better than 50% chance for me, right? As long as I had more than 23 people in the room. So this is kind of a byproduct of if things are independent, we use that independence rule, find that probability of the intersections. Kind of a fun example. The results seem, I think, counterintuitive. I don't know, I thought it's a fun example. It kind of, when you first work through the numbers, you're like, there's no way this is true. Yeah. Really? There you go. Right? So it's like, you obviously, at any given time, you could be wrong. It's an 80% chance, right? You're going to be wrong 20% of the time. But in a class, even 35 is not that bad. I think I did this for my other sections, and there's like 40 people enrolled, and it gets even higher. One time I had a big section of like 65, and this is like close to like 90, like this is over 90%, and people are like, there's no way. But yeah, kind of a crazy counterintuitive result. All right. I think that's all I have for today. I should be able to get this afternoon some of those practice exam videos recorded and posted up there on YouTube along with today's class. If you have any questions as you're working through those practice exams, feel free to kind of zoom in and meet with me. I had someone kind of even approach me, say, like, if I do all my work, I don't know how to like approach the Zoom meeting because I can't tell you what I did. A really good way around that, it's like light bulb click when I told them, is we'll take pictures of your work. Then if you meet with me on Zoom, you can always just share your screen with me and I can see the work that you've done, right? So if you have any questions over that Excel homework, also kind of reach out. Other than that, I will see you guys on Friday. Have a good rest of your day.